Okay, so I started like a few months ago together with Brian and Vasil. And along my other tasks, of the main is try to work out root modularization. And oh, sorry. So, like, shortly, if to check the history of these efforts for modularization, it started like in 2007 by René with his boot, and still there was no really decision what to do. For me, what I see as my goals is just to try to review root subsystems and their dependencies, select something like small, hard-like part of root, which could be fundamental for modularization process, and then try to make root more friendly for plugging new developments, to adopt root source code for plugging new things, checking out what you want, building only what you need, and reusing intermediate and final deliverables. Which benefits actually could be it's that user can get as a final product. Root is as a much more smaller package, which is containing services that they only need, and they can plug whatever they want after. Make it so it will make root much more friendly for the users. Also, it will help more efficiently managing dependencies, which is like really a lot for root. Also, root libraries and external libraries, and simplify also the adoption process for new and for example, external contributions in the root. So, if to start like from the beginning, from the scratch, like example, imagine you are talking with 4 developers, what is modularization, and for sure you will get at least 5 replies, maybe, I don't know. And what we need to start is about base layer, how actually root define the model, and maybe try to allocate few simple root functionality examples that then we can recast them as a model. And this could also get you a nice feeling how model or package would work before even starting to imagine how they could be managed. And also the goal is like presenting on such forums or meetings. It could be also nice to have a mechanism for feedback and to collect more viewpoints for this. So I was checking like how was actually big open source products they had the process of modularization, and there is like 2 available examples for me that I found in web. It's LibreOffice and Xorg, and you can go through the links and you can see that if it was successful or not successful. I hope we will not repeat the new story. So something that I was just studied looking around about modularization. So I see there is maybe 2 directions how we can actually go ahead. First one is we can add some external support to plugging new developments, new contributions that doesn't require changes in records. The second one is more complex, and probably it's something that I would like not to talk still, is how to extend root interfaces to be able to plug new developments or something like this. And for sure, we need to have something like a package manager and something alternative and try to work in both directions. So I start to look in the package managers as just an inspiration for new tools. So we are not talking about to have our own package manager. It's just that most of package managers, they have a lot of nice ideas which could be, it should be needed to think at the beginning. So I took check Homebrew, Portage, and Spark. Homebrew, it's very nice because you have these recipes and it's extremely easy to follow up and check what's going on. Partage is nice because it has actually Git integrated, so you can easily, perform different Git actions and check out on repositories. And Spark, it's interesting from the point of view that it's a help to support multiple versions and configurations of software, and it's already used widely in a PSFT for LCG packages. So could be the ideas used in Spark could be also useful for this project. Then was
I wouldn't really say it's widely used.
Well,
under investigation, probably is more.
Yeah, under investigation. It's still, yeah. And so then I checked out two proposals of Python packaging system, PEP 425 and 427. And it was interesting, actually, the way, I will just remind PEP 427 is basically a standard, the format, zip format, which is with a specially formatted file name and particular extension, which is used by, could be used for installation packages. And what is nice, so we have a tag 425 is a standard proposal defining tags for Python. And you see that there is also some similarities that is already used by LCG packages. Also nice that they have requirements files, which is probably could be really helpful. And also nice idea to having cache, and probably it's something that I should look into. Then also I check sorry, it's too blue, probably hard to read. It's just the simple examples of configuration files and metadata files, which is probably very simple to maintain and in the same time they're efficient. I was looking also in the R, and so for R, its packages are really fundamental units, and the R doesn't, as I understood, R doesn't have any responsibility for plugged packages. And the coolest part for me is that each of these packages, they actually have a set of the test that if you install it and the test is not passing, basically R will not allow you to plug it. So it will, R by itself have self-defended system for malfunctioning packages. So there's like a few ideas probably how it's possible to help to modularize root. One of our proposals is about clean integrated tool from Vasil, when you basically include some header of the package that you didn't have, and then yep, magically you have it there. The second one is from Perium. We were discussing about probably to have something like tinstaller, that class that will help root to work with external packages and also help to build them from scratch in case. And there is like a lot of questions. Could it be similar to Python package management tool? Where to put it externally, inside core, inside clean? So my next steps now is to review a root minimal option to check out this core, let's say core-like subsystem of root. Review maybe dependencies if there is some problems, and try to make a prototype allowing to upgrade root minimal with a few extra options and dependencies. So yeah, it's very short, and thank you, and I'm really looking forward to see any of your ideas and suggestions, and yeah, please. I hope it's not my last presentation here.
Okay, thanks. Comments or questions? Anyone?
I have a simple question. So you mentioned about one of the suggestions was when you have a header and you don't have currently this header, then load this package. What's the relationship between the header and the package?
Could you repeat the question since he's far from the microphone?
We'll move on.
Can you hear me now?
Yeah.
Okay. This might be a bit, I don't know, not stupid. In C++, there is no such notion as package, so that's why I'm asking. So one of the suggestions was when you have a header, you have to load, and you don't have this header basically, then you have to install or whatever, some package. So the question in here would be, what's the relation between the header and the package? I mean, if you said a header and a shared library, then I could understand that. But if you have a header and a package, and what is a package then in relation? So.
Can I try to explain it because it is kind of coming from me?
Yeah. Right.
So the relationship normally that we think of is one header and the library. But the package.
Vasil, we can't hear you.
The package
Thank you.
could be a superset of more than one library, right? When you have normally you can have one-to-one relationship, but that doesn't preclude to have one-to-one relationship when you have this is a package which does more than one library does.
So just a collection of those.
Yeah, it could be a collection. In root, as a matter of fact, we have this notion when we have a database or a description of which header belongs to which library, and this goes recursively. So in the cases where you request a header file, root on the backstage would also pull in the relevant libraries, even though in certain cases you will have a dependency between headers. So this header includes this one, and this one comes from some other library. And in this case, you will get a sort of a virtual package because of this recursiveness of the logic. You will get the first include coming from this, and then if you have potential includes that are described in some other library, you pull in also those libraries.
Thank you.
Sure.
Other comments or questions?
So since I see a couple names on the list that are people that are kind of from the experiment side, I'd be curious to see what kind of, to hear what kind of demand or discussions along these lines that people hear from within the experiment, either the experiment proper or from people who are analysts. You know, is this something that gets chatted about or discussed in hallways over beers?
Well, you know, for within CMS, although I haven't looked at it recently, within CMS we've always managed sort of by hand subsets in terms of loading things, right? And sort of just generically in the build system, there's always been this sort of by hand management of these subsets. In the analysis world, I mean, this has been the trick, is how to define the subset. Clearly, the root IO subset comes up in contexts like the studies, the sort of big data studies, right?
But the last news from the community was mostly in Amsterdam when we talked about it, where it was generally said that it is difficult to plug in new things and replace things in root.
I also remember hearing desire for modularity with
The general statement has been there for a long time, but it's specific applications that drive things. I was there on that.
Yeah, okay. Yeah, I mean, what I was thinking was, you know, whether we wanted to focus on kind of organizing modules inside root, which may not be very user visible, or the sort of things that Vasil was mentioning, that, you know, having some sort of auto loader that's a lot smarter, which would be a very user visible feature. And sorry, I think I talked over Ollie there.
Okay. Other thoughts? I mean, we'll come back to this at some point in the next month, of course.
Well, I just wanted to mention that mostly in root we have this modular sort of approach because the components are there. the missing bits and pieces are that we are actually most of the time using them together. So it will be reasonable if you start dividing them as they were initially designed for. We have a minimal set of libraries where you can bootstrap reasonable part of root, but it's just that they are not tested, and maybe there are things to fix here and there. So it just needs users and some use cases.
Also at the build time stage, we're building a small fraction of root as part of the modularity.
Yeah, we even have this option -g minimal on, which are not actually testing. So this is supposed to.
How minimal is the idea?
So yeah, I think we can try to review it or something. Yeah, it's like supposed to run hsimple. hsimple, for example.
Yeah, I think it's the minimal I/O operations. So you bootstrap root where it gets prompt and basic services like interpreter support, and you can do, I think, I/O on tuples essentially. This will be the minimal thing that I assume would have. If we don't have, we should aim for something like this. And then from that point on, the idea is to start building on top a little bit based on the demands of the users, what they want, and then you probably can get it from somewhere or build it for them.
Okay, so why don't we move on? Who is next? Brian? What's up next?
Yeah, and I can drive, or David Lane can drive. David, do you have a preference?
You're the speaker, so it's up to you.
Oh, why don't you drive? I don't have it. So as you're going there, what I wanted to do was give a quick update and kind of share what happened at last week's root.io meeting. You know, since it actually seems we have a lot of overlap between the people from the root.io meeting and our root.io workshop and this meeting today. I'm going to kind of jump through some of these slides. So go ahead and go to the next slide, David. And try to make short work of this so we can get onto Jim's presentation. But there are some other folks here that weren't there, so feel free to stop me if I go too fast and lose you. Now, this was about a 2 to 3 hour meeting. I'm trying to do this in 20 minutes. So many apologies for those who presented, and I skipped or summarized out something really important from your work, and again, feel free to interrupt. So kind of the highlights I think that generated the most discussion last week was progress on various compression formats, bulk I/O, and work on parallel file merging, both from the kind of the T-data frame point of view and from CMS as presented by Dan Riley. And then I wanted to talk a little bit of the things we want to start experimenting with for the next 6 months versus things that we are to nail home for the December release. All right, next slide. So on the topic of compression, we are in the tail ends of adding support for LZ4 for root. This includes backports to all active release branches, which is more difficult than it sounds because it also means fixing up test cases, fixing build scripts, fixing up the other version of the build scripts, and so forth, on and so forth. So this a lot has been spearheaded by Oksana to nail down all the loose threads. And the other one that we're hopefully nailing down is our work for the default Zila performance. If you remember, patches from Cloudflare, for example, are 4 times faster for compression at level 9 for zlib, but really it only worked on x86 64-bit and fairly new processors compared to what you see on the grid. So David started, and Oksana is continuing work to make this more widely usable and something that we can just have in as part of the root build. So along this route, and we reported this during the summer, you can actually have lots of interesting fun trying to figure out which version of zlib root is using. Depending on the order that you invoke stuff and how you built root, it seems that there could be 2 to 3 versions of zlib and root. So we're trying to either trying to get down to 1 version of zlib, or at least make sure that we consistently use the same version of zlib in the same places and not have it depend on, for example, when LLVM gets loaded. So this is actually where the bulk of the work remains here, is trying to, we kind of got into this rabbit hole of mini zlibs within root. So going on to the next slide. So this is from a presentation from Jim, and the highlight of this is kind of things we've seen before. LZ4, when reading, performs similarly to uncompressed data. LZ4 write speeds are similar to the current root default, and the file sizes result in about 15% larger. And that 15% number will fluctuate widely based on exactly what's in your data. So that's just kind of an approximation. Based on this results and the prior results leading up to this, one thing that we did decide at the meeting is right after root 612 branches, we're going to make LZ4 the default. That means since we think this is best when used with analysis in tuples, this will be the default for analysis in tuples. And we only need, for example, the 4 LHC experiments to turn the default back to or to turn their internal defaults back to zlib or whatever they want to use for their EDM models. We decided to do this, so that will land in 6.14 in terms of the change to defaults, and we decided to do this to give experiments more time and the older backport versions more time to propagate. So this is something that I think is going to make a significant improvement for analysis users that they won't need to think too much about. Next slide. So in terms of bulk I/O, if you remember, bulk I/O is an approach that involves root libraries once per event cluster, which for n tuples might be hundreds of events instead of per event. And this is applicable for simple object types, but potentially very large speedups for these object types. And we've kind of noticed that simple objects are what is in analysis anyway. So over the last summer, or since the summer, bulk I/O has kind of matured enough to build some high-level interfaces. It has matured enough to do realistic performance comparisons. We'll show some for CMS Nano AOD, and to get it into a reviewable state and put it into a pull request. Now, since this does touch a lot of the lower layers of root, there's going to be kind of a lot of rounds to get the pull request merged. So I'm aiming to get this into the 6.14 release. Next slide. So this is the same tests on the same platforms, looking at the CMS Nano AOD again. If you remember before that the reading in terms of event rate topped out at about 15 kilohertz. Here, using the bulk I/O interfaces instead, the same reads top out about 500 kilohertz for completely uncompressed data, and maybe about half of that for compressed data. Either way, it's over a factor of 10 increase in throughput for analysis work, and it's for me actually kind of encouraging in some of Jim's more detailed tests, he's actually been able to show that you start to see the CPU cost of what the user is doing. You know, you can tell the difference between simple additions versus trigonometric functions. So we're no longer IO limited here, and that's, to me, quite exciting based on where we started. Here it also makes, this graph also makes the penalty for LZMA quite obvious, where you pay a factor of 2 in terms of event rate for LZ4, going all the way to those really high compression ratios with LZMA. That means there's about a factor of 100 for read performance. So as folks are designing formats meant to be read quickly and used for analysis, you really will want to think twice about that extra space savings from LZMA. Next slide. So in terms of parallel merging, this has been something that Dan Riley from CMS has been pushing. So this is something he did a nice presentation in the summer on, talking about how root IO, output part of root IO, limits CMS scaling, because to output to a single file, we can only have one thread at a time. And you can see here on the right is one of Dan's graphs showing the number of active threads at any given time. And you see these periodic chunks where it goes down to only one active thread. And that typically is the output bottleneck for event clusters. So root is currently the dominant source of output stalls because we're writing to a single file that needs a big lock. Next slide. So CMS is working to refactor their output module that allows multiple writers that have a limit somewhere between 1 and the number of threads in the application. So in this example, we'll show some slides, show some pictures from Dan where he tested with 4 output threads. And we use this to manage a pool of output buffers using the T buffer merger class. So next slide. So T buffer merger, this is also being heavily used for T data frame, which allows a lot of implicit multi-threading, allows root IO to basically use one output file, but give it prepared, merge in or have data buffers owned by individual threads, and then push this all into a common queue owned by a single object that then has a separate output thread writing out to disk. So over the last couple months, a lot of the work in T-buffer merger has been along the lines of improving scalability here by reducing some hefty locks for serialization, and it's been worked toward making sure that the output thread doesn't do as much compression work, so all the CPU-intensive parts stay within TBB. Next slide. So here's the corresponding happy picture with comparing the stalled or the original case with LZMA 9 and then the output case, or the resulting case once we have multiple threads doing output. And as you can see, the stalls where there are no threads running just about disappear. And then here the statement as at 12 threads for this mini AOD production, scaling efficiency goes from 90% to about 97%. Next slide. So another really interesting discussion involved around a proposal from Jim to look at or better use object stores. And as opposed to looking at completely non-root formats or having a foreign interface, Jim proposed and we discussed ways we could have the T-file and T-tree interfaces actually access object stores or project object stores by storing individual T-baskets. And we think that the basket level might be a reasonable abstraction to interact with the object store as opposed to particularly the individual event level. So this generated a lot of interesting discussion and particular ways to show a series of simplified capabilities leading up to the full vision here. All right, next slide. So some up and coming important aspects. One thing we're going to put into 6.12 is we're going to have a new mechanism for detecting forward compatibility breaks. So that way, if we have new feature XYZ in some version of root, older versions of root that don't have the necessary reading code will return a clear error message and refuse to try to deserialize the data with a new feature. And this is as opposed to crashing or even worse, potentially returning incorrect data to the application. So the idea is that this allows us to start, or it gives us a better pathway to add experimental features instead of avoiding this at all costs or having each feature come up with their own forward compatibility mechanism. And the idea is we'll work through a couple ideas that we have, disable them by default in the Root 6 series, and that those that show lots of promise or actual really appreciable improvements will be able to enable by default for Root 7. So this doesn't add much end user improvement itself, but really unlocks a lot of stuff. Next slide. So example here, and I think this will be the first one, and I think we'll get it in time for 6.12, is skipping event entry offsets. So this tells us where the beginning of an object is in the byte buffer. And turns out a lot of this information is redundant and doesn't need to be written out per branch. Many branches can share this information. In the extreme case, if you have a split object with 40 attributes in it, this data might actually be encoded into the file 41 times. So we're trying to get that down to 1 time. So the forward compatibility break we're doing here is if we can detect that this array can be generated at runtime upon reading, we're going to skip writing these into the file. Now, for some formats, they have pretty efficient compression of these duplicate data, and we save really modest amounts, kind of 5, 6, 7% level. But for something like LZ4, we find that this is probably going to save about 18% of the overall file size. And for some people who are looking at using LZ4 but are kind of recoiling at 15% larger files, this will allow us to recapture quite a bit of that. We think we'll see how this works as we merge and test further. Next slide. Z-standard is an interesting new compression algorithm. It's interesting in that it has a wide range of performance characteristics, but it's more interesting in that it actually has a very nice API for interacting with compression dictionaries. And in fact, Facebook developers report some really massive speed-ups and rates and massive improvements in compression ratios doing these techniques with something that looks a bit like what root baskets look like. So I don't think we'll get as good a speed up as I'm about to show, but even a quarter of the improvements that they saw would make this a really huge improvement for root. So going to the next slide. So this is Z-standard compressing a corpus of 10,000 1 kilobyte entries with and without compression dictionaries. And I think the most intriguing one is the one on the left here, where the compression ratio goes from 2.8 to 8.3. So about a factor of 3 improvement in compression ratio. Again, this is fairly unlikely this is what we'll see for root files, but anything even approaching that is going to be really a welcome improvement. This is at the ideas generating phase, and we've got quite a bit of work to do before we can say what this is going to actually achieve, but this is something that will be going over the next couple months. Next slide.
Brian, so the API offers reasonable support for actually generating dictionaries based on the algorithm? Because that's the thing that was partially missing, I think, elsewhere, is they could use dictionaries, but how to make them was less clear.
Yeah, that's the thing that really has caught my eye in terms of making this practical. zlib can do dictionaries. LZMA, the format can do dictionaries, but doesn't actually expose it in the API. But before Z standard, I never actually saw anything that helps you generate these stupid things. So this will possibly be an enabling technology where we really couldn't touch this before.
Okay, thanks.
All right, next slide. So just to kind of summarize here, this is the last slide here. I think what we'll see in 6.12 is this forward compatibility break mechanism, skipping offset entry writing. We're likely to see some improvements for parallel asynchronous unzipping, and then for this T buffer file, I always mess up the name, but the improvements, parallelism, that CMS and T data frame we're looking at we should land at 6.12. Things that are a little bit further out is the initial version of the bulk IO, the improved zlib, and any sort of experiments that come out of this work for Z standard. All right, and that's all I had for the discussion or summary of 2-hour discussion. So. Again, if you were there and I missed your favorite topic, feel free to chime in. Thanks.
All right, thanks, Brian. Questions or comments for Brian? It was quite clear, especially for people like me, that I had a conflict and couldn't make it meeting. So look through the slides, but the summary actually helps. Okay, so why don't we go on to Jim? You share your own slides, Jim?
I think I'll do that so that I can do arrow keys.
So Jim is going to share his own slides, David.
Okay, so I'll begin. I'll be talking about the root format specifically. So let me start with an obvious statement. Root is a file format. Here's how it relates to quite a lot of other file formats. So it's like HDF5 in that it organizes objects into file system-like structure. It's like Avro in that it defines the structure and the classes it stores, the schema evolution. It's like Parquet in that it can split classes and columns for efficient access. Although the way that it splits it is more like Arrow Feather. It's like Pickle in that its data model encompasses a whole language, C++ rather than Python. It's like FITS in that it was developed by a scientific community for that community, but it has this union of all these features. It's quite a lot of things, but it's unlike most of the above in that it doesn't have a formal specification. So looking through most of the formats I just mentioned, I looked around to see which ones had specifications, and really most of them did. And also counted the number of implementations. And I found actually an interesting trend. You sort the file formats by their inception year, and that correlates strongly with the number of implementations, which makes sense. The longer something has been around, like FITS has been around forever, lots of astronomers use it, so there are a lot of different implementations on it. You can all find them on NASA's webpage. 38. The newest things that came out last year, like Arrow Feather, there's a much smaller number of implementations simply because it hasn't been around. And now the thing that breaks that correlation is that Root and Pickle here don't have a completely encompassing specification. So, for instance, in Pickle, you can find documents that describe how the implementation changes, which is really different from a specification. And in Root, you can find some information about the headers of certain types of classes, like tfile and tkey, but these are not fully encompassing the same way that they are for the other ones. And then the number of implementations for those two, even though they are old, is much smaller, which makes sense, right? If there isn't a document describing exactly what each byte means, it's much harder to write a reader for it. So there are pros and cons. We've been talking about this in the Root IO group. Specifically, this came up because of talking about alternate implementations of Root IO and the questions that the people who are working on these are raising questions that would be normally found in a specification. Now, why not specify? Well, if we had a document first, that would inhibit development. We wouldn't be able to experiment with exactly the things that Brian just described in the last talk. Also, if it's just a human readable document, those get out of date without a lot of file format lawyers always checking. The personnel to develop Root features are already limited. The streamer info actually specifies most of the classes dynamically, so a lot of that, the thousands of classes in Root really don't have to all be specified. And the Root C++, Root has a model where the C++ implementation is really primary. So what Root C++ does is what the root file is. But on the other hand, there are benefits to specifying. It can make for better data preservation because you don't necessarily need a particular version. Root has great backward compatibility, but say there's a bug or something that only a particular version, old version of Root can read a particular old file, you might get into a case where preserved data, you need to resurrect some old version of the software. Specifications clarify invariants that are hard to code or they're not local in the code. It can actually help the process of adding new I/O features because we can see what's there and what's changing in a more concise way. It allows alternate I/O projects to maintain themselves so that the information about a new feature doesn't have to be actively propagated to them. And also, this point about it inhibiting development, specification can be descriptive rather than prescriptive. So it would even be valuable to have a document that describes what's there rather than what should be. So I've mentioned the alternate implementations a few times. I should list all of the ones that I know about and their various purposes. Most of them are about enabling Root in different platforms, such as Spark. That's the reason that Root4j exists, or Go. That's the reason that Root IO in Go HEP exists. And I have an implementation, which is why I'm in this game. Uproot is a Python implementation of Root IO. It implements this bulk IO style NumPy access on a shorter time scale than 614. Also, I found it seemed like a marginally good reason to start. Since I built it, I've been thinking it was a really good idea to do this because it has helped me understand Root IO quite a bit better, to look at it from a different view. So let's look, just to show kind of what this looks like, look at some sample code that are just cut out of Uproot. There is, in the middle of a class, when you're moving some file pointer through, you want to get fn bytes, f version, f object len, f date time, etc. out of the file and into active variables. And so we do that by saying, oh, they're big endian, that's the exclamation point. They're 4 bytes, 2 bytes, 4 bytes, 4 bytes, unsigned, 2 bytes, you know, stuff like that. And this all is very imperative. You start at the beginning, you read some bytes, you read some bytes, you read some bytes, and you get to the end. And if there was a version branch that you didn't know about, like if I didn't know that F version greater than 1000 means that you should load these as 64-bit, then you get off by 1 or more, and it's all just wrong from that point out. So this is imperative code, but it doesn't have to be. What I've described here could be described by a declarative DSL. So here, after I had the Python implementation, so I knew what's there, I went ahead and tried to, and expressed this all in a declarative specification to see how hard that would be. The idea here is that this is a specification. It's something that a human can just read, and it has abstracted away most of the code, you know, the concerns that code has to have about running at runtime. But at the same time, this document is executable. You know, you see that this is this machine-readable thing that you could read this, look at a root file, and determine if this description is right. I did it in YAML. There was some choices about what to pick for that. It is a declarative data language like JSON, but it's optimized for human input. So it's often used for configuration files. That's why it looks like this. And then, of course, YAML by itself is not enough information to interpret this. So we have this YAML syntax that we then interpret what these fields mean. And then that acts like a DSL, a domain-specific language, for describing root layout. So as I mentioned, it's executable. You can run it through unit tests and check that it works. It's one thing that's nice that distinguishes it from code is that it says nothing about eagerness versus laziness. So we can leave that to the implementation. It resembles the streamer information apart from the fact that it can have if-then branches. And we can add features as needed if we're going through the root format and find that this data this DSL is not flexible enough. We can just add features to it because we control it. So showing a couple more examples, I have ran into cases where we need to seek to particular places, so I added a semantics for that. Ran into places where we had to post-process some of the values that came in, so I added a syntax for that. Had cases where we needed something like an array of objects, so I added something for that. So basically just adding to this DSL as we needed features to read root. So I want to say a special point about eagerness versus laziness, because this is like one of the most important features of root I/O. It's not like a PNG file where you just read the whole thing in and then do something with it. Generally, every time you approach a root file, you want to read part of it and probably not all of it. So in C++, the root immediately reads the first T directory, and then based on what you pull out of it, some T keys, and then based on what you pull out of that, the data behind the T keys. Same thing for baskets in the tree, all responding to user requests. But in Python, actually, I wanted to go even further than that because there is a cost associated with creating strings and other non-primitives. So, so I wanted them to be behind properties. So the choice of how eager or lazy depends on implementation. So naturally, they shouldn't be part of a specification. And so as a demonstration that this YAML specification is not, can't only be interpreted in an eager mode, I implemented a purely lazy version of this, something that looks at the YAML file and then with 100% laziness doesn't read anything until you ask for it. And it's possible. So then this specification has really abstracted out the question of eagerness versus laziness. Now, about the streamer info, most root classes are specified to this degree, not in a document, but in the root files themselves. And this, to my surprise, coming at this, I didn't realize it includes some very, very basic classes, not just things like TH1s, but also T-trees, even T-list, T-named, T-object arrays, things that are really in the core of root. Basically, anything that wasn't strictly necessary to read the file would be specified by the file. So there's no reason for a specification to duplicate this. How far can this documentation go? Brian expressed a wish list. The container classes to bootstrap to the point where we can read streamers. So this is basically what I've already demonstrated. How the STL classes are streamed. So the STL has documentation for how these should be read out, and they are written exactly that way into the root files. But we may want to re-express that STL documentation in this format just so that it can be a unified format. Root has custom framing for compressed blocks, and this would be an ideal place to explain what all those 9 or 17 bytes mean. How streamers get generated from classes, how classes are split into branches, how cross-references are keyed by byte positions and relative to what origin. The last bit could be hard to express declaratively, but I'll think about it. So, conclusions. A non-prescriptive specification for how root I/O works would benefit data preservation, the process of changing root, and alternate implementations. Such a document can be an unofficial description, just like I didn't explicitly point it out, but thrift, the file format thrift is missing a specification, so somebody in industry added one. And it's completely unofficial and descriptive, but it's one of the first links in the web search. A specification can also be executable to verify that it's correct on test samples and make sure it doesn't get out of date. And I began a demonstration level project of some core root classes in YAML. And they can configure readers anywhere on the eagerness to laziness spectrum by demonstrating that you can implement the purely lazy because implementing eager is much more straightforward. So this is where that repository is, and yeah, I intend to use this kind of an approach. I didn't get very much feedback from the other alternate implementation developers. So I intend to use an approach like this in future versions of Uproot so that it can double as a specification. So, any questions?
Yeah, so if you look at a practical file, somewhere along the lines of a event data format at the hard end, or maybe an analysis in tuple at the easy end, do you have a feel for what percentage of the file you could read at this point?
With the demonstration, I can only read TH1s, actually TH1F. For the demonstration.
Okay.
And then if I integrate it into Uproot and bring the feature parity back up to where it currently is, then it's all of the non-destructive branches, just like bulk I/O does. But then it would be possible to go further than that, but not with any kind of performance in Python, unless we use like Numba or something. But for specification, performance is not the point. Other questions? Okay.
Okay, thanks everybody. And a little bit long, but I'm not sure we ran on exactly on time. All right, thanks everyone. Bye.
Thank you. Bye bye.
Thank you. Bye.